Network configuration and traffic management. Assigning IP addresses. Static addressing. Overview involves assigning a permanent IP address to a device akin to a fixed home address for consistent and long-term identification. Dynamic addressing. Description utilizes DHCP Dynamic Host Configuration Protocol for assigning an IP address to a device temporarily, much like assigning a changing hotel room number to each guest. Boot Protocol Boot. Functionality: an older protocol that aids a computer in locating its IP address and other necessary network information upon startup. Automatic Private IP Addressing. Analogy: similar to a ship navigating by stars in the absence of a compass, this method involves a device assigning itself an IP address when a DHCP server is not available. Identifying MAC addresses. Explanation: a MAC Media Access Control Address serves as a unique identifier for network interfaces, similar to a serial number for a device's network card, crucial for local network activities. NAT and PAT Address Translation Methods. NAT Network Address Translation. Analogy: NAT functions like the receptionist of a large office, directing calls data packets to the appropriate department device. It translates private IP addresses into a public one for external communication. PAT Port Address Translation. Description: PAT extends NAT's capabilities by managing specific ports, analogous to handling extensions in an office's internal phone system. SNAT Source NAT and DNAT Destination NAT. Variations: these are specialized forms of NAT, dealing with the source and destination of network traffic, respectively. Routing and switching management. The default gateway. Role: previously explained as the primary exit point from a local network to broader networks. Routing tables. Function: act like a city map for network packets, providing directions to reach their intended destinations. Static routing. Concept: involves setting predetermined routes for network traffic, similar to establishing a permanent path through a forest. Default route. Usage: the fallback path network traffic takes if no specific route is available for a destination. Switching methods. Approaches: various methods switches use to send frames across the network, such as store and forward or cut-through techniques. Packet and circuit switching. Packet switching process involves sending data in small units called packets over a network, where packets can travel via different paths, akin to cars taking various routes to avoid traffic congestion. Circuit switching method establishes a dedicated pathway between 2 points for the duration of a connection, much like creating a private road for a specific journey. Comparing switching methods. Analysis involves evaluating packet and circuit switching based on efficiency, reliability, and scalability, similar to comparing different transportation methods for speed and cost effectiveness. This structured format provides a comprehensive understanding of the processes and methodologies involved in network configuration and traffic management. Network engineer training. Network configuration and traffic management are integral components of ensuring smooth, efficient, and secure network operations. Understanding and implementing various aspects of these processes are crucial for network stability and performance. Network configuration aspects. Assigning IP addresses. Static addressing involves assigning a fixed IP address to a device, providing consistent and long-term network identification. Dynamic addressing utilizes DHCP for assigning IP addresses temporarily, enhancing flexibility and efficient address utilization. Boot Protocol Boot, an older protocol aiding in network booting and IP address assignment. Automatic Private IP Addressing (APIPA) enables a device to assign itself an IP address in the absence of a DHCP server. Identifying MAC addresses. Every network interface has a unique MAC address, serving as a permanent identifier for the device's network card, crucial for directing local network traffic. Traffic management techniques. NAT and PAT address translation methods. NAT network address translation works like an intermediary, translating private IP addresses into a public one for external communications, ensuring security and efficient address utilization. PAT port address translation extends NAT capabilities by managing specific ports, allowing multiple devices to share a single public IP address. SNAT and DNAT, specialized forms of NAT that handle the source and destination of network traffic, respectively. Routing and switching management. The default gateway acts as the primary exit point from a local network to broader networks. Routing tables provide directions for network packets to reach their destinations, similar to a city map. Static routing involves setting predetermined routes for network traffic. Default route serves as a fallback path for network traffic when no specific route is available. Switching methods. Packet switching sends data in packets over the network, allowing for diverse paths and efficient utilization of network resources. Circuit switching establishes a dedicated pathway between 2 points for the duration of a connection, ensuring a consistent and uninterrupted flow. Comparing switching methods involves evaluating packet and circuit switching based on efficiency, reliability, and scalability. Importance of network configuration and traffic management. Proper network configuration and traffic management are essential for maintaining network integrity, performance, and security. Assigning IP addresses correctly ensures that devices can communicate effectively, while MAC addresses play a crucial role in directing traffic at the local network level. NAT and PAT are vital for conserving IP addresses and protecting internal networks, whereas routing and switching techniques dictate how data is moved across networks. Together, these components contribute to a robust and dynamic network infrastructure capable of adapting to varying demands and ensuring continuous, secure communication. For network professionals, understanding and effectively implementing these aspects is crucial for optimizing network performance and reliability. Network protocols and switch management. The Spanning Tree Protocol. Function. This protocol prevents network loops by creating a tree-like structure within the network. It ensures a single active path between two network points, analogous to creating a family tree to clearly understand relationships. Interface configuration and switch management. Overview involves the setup of network interfaces and the administration of network switches, similar to organizing individual workstations and managing office resources. MDIX. Description. MDIX refers to a type of port on a switch that allows connection to another switch or hub without the need for a crossover cable, akin to a universal charger for various devices. Trunking. Functionality. Trunking allows traffic from multiple VLANs to move across a single link, comparable to a main road that connects several side streets. Port mirroring. Purpose. Used for sending a copy of network packets seen on one switch port to another for monitoring, similar to installing a security camera for observation. Port authentication. Security aspect provides a layer of security, ensuring only authorized devices can connect to the network, like bouncers checking IDs at a club entrance. Power over Ethernet PoE and PoE+. Capability. PoE allows electrical power to be transmitted along with data on Ethernet cables, enabling devices to be powered via the network cable, similar to phone lines carrying both voice and power. MAC address table. Role. A list within a switch that maps devices' physical addresses to their ports, functioning like a detailed guest list at a reception. Switch management. Management tasks involves maintaining and monitoring network switches, crucial for ensuring smooth network operation, akin to overseeing a team in a workplace. Managed and unmanaged switches. Comparison. Managed switches offer greater control over the network, while unmanaged switches are simpler, plug-and-play devices, paralleling the difference between smartphones and basic phones. Quality of service costs. Network priority. a feature that prioritizes certain types of network traffic to maintain performance, like designating fast lanes for emergency vehicles during heavy traffic. Traffic shaping, traffic management, the practice of regulating network data transfer to optimize and ensure efficient data flow comparable to synchronizing traffic lights for smoother traffic. Access control lists ACLs. Traffic control. ACLs are sets of rules that govern the incoming and outgoing traffic in a network, acting as gatekeepers to allow or deny traffic, much like a bouncer's role. ARP and RORP. Address translation. ARP Address Resolution Protocol converts IP addresses into MAC addresses, while RORP Reverse Address Resolution Protocol performs the reverse process, akin to matching names to faces and vice versa. This structured overview provides insights into various aspects of network protocols and switch management, using everyday analogies to elucidate complex technical concepts. Network engineer training. In the bustling metropolis of Network City, a network engineer is akin to an urban planner and traffic manager rolled into one. Every day, they navigate the complex web of protocols and switches that keep data flowing smoothly and securely through the city's digital streets. One morning, as our engineer sips coffee, they review the network's topology. They liken the spanning tree protocol STP to the city's traffic lights and signs, preventing data packets from endlessly circling roundabouts and creating gridlocks. By ensuring a loop-free and efficient path through the network, STP keeps the city's data traffic flowing smoothly, much like a well-coordinated traffic system keeps cars moving efficiently through city streets. As the day progresses, the engineer turns their attention to switch management. They configure interfaces and administer switches, laying down the digital roads and pathways that connect different districts of Network City. With NDIX, connecting these switches is as seamless as snapping together modular pieces of a toy track. No need for special crossover cables or complex configurations. Then comes the task of managing trunk links, the city's highways. Just as a highway allows multiple lanes of traffic to flow between different parts of the city, trunking permits data from multiple VLANs to traverse a single network link. Our engineer ensures these highways are wide and robust enough to handle the city's growing data traffic, preventing bottlenecks and ensuring a smooth commute for all data packets. Midday brings a new challenge, setting up port mirroring for security monitoring, akin to installing CCTV systems in vital city areas. This allows the engineer to observe and analyze traffic, identifying any unusual or malicious packets that might indicate a security threat, much like how security personnel monitor video feeds for suspicious activity. In the afternoon, the focus shifts to power over Ethernet PoE. Just as modern cities look to integrate power and data cables into sleek, efficient units, PoE allows the network to power devices through the same cables that carry data, reducing clutter and simplifying infrastructure. It's a game changer for deploying devices like IP cameras and phones, making the network more streamlined and versatile. As evening approaches, the engineer reflects on the importance of quality of service costs and traffic shaping. In the same way that cities might prioritize emergency vehicles or regulate traffic flow to prevent congestion, costs, and traffic, shaping ensure critical network applications receive the bandwidth they need and data flows remain smooth and efficient even during peak hours. Finally, as night falls, the network engineer considers the role of access control list ACLs and address resolution protocols like ARP and RORP. These tools are the gatekeepers and directory services of Network City, determining who gets access to which resources and ensuring every device can find its way to the correct destination. In Network City, the job of a network engineer is never done. Each protocol and management task represents a piece of the intricate puzzle that keeps the digital metropolis thriving. From preventing traffic jams with STP to powering devices with PoE, every action they take ensures the city's data continues to flow efficiently, securely, and reliably day after day. It's a challenging but rewarding responsibility, knowing that with every configuration and every line of code, they're shaping the digital landscape of Network City. Overview of common networking devices. Firewall. Function. A firewall acts like a security guard for your network, checking the data entering or leaving against a set of rules. IDSIPs. Role: Intrusion Detection Systems (IDS) and Intrusion Prevention Systems (IPS) monitor and analyze network traffic for suspicious activities akin to a surveillance system. Router. Analogy: routers function like mail sorting centers, directing data packets to their intended destination across multiple networks. Switch. Description: switches serve as office network hubs, connecting various devices within a single network to facilitate communication. Hub and switch cabling. Functionality: cabling is the physical wiring that connects hubs and switches, forming the infrastructure for data travel within a network similar to veins in a body. Multi-layer switch. Capability combines the functionalities of both switches and routers, handling data traffic efficiently in large networks. Hub. Basic operation. A hub is a fundamental networking device that connects multiple computers but sends incoming data to all devices indiscriminately. Bridge. Purpose: bridges connect two separate network segments, enabling them to communicate as though they are part of the same network, much like a bridge connecting two communities. DSL and cable modems. Usage: provide internet access through phone lines, DSL, and television cables, cable modems, acting as gateways to the internet. Access point. Function: offers a wireless connection to a wired network, similar to a Wi-Fi hotspot in a public space. Media converter. Role: translates data signals from one type of network media to another, such as from cable to fiber optics, ensuring compatibility. Voice gateway. Operation: allows voice communication to travel over the internet by converting analog voice signals into digital data. Repeater. Analogy: functions like a relay station in a broadcast network, extending the reach of a network by amplifying its signal. Wireless LAN controller. Management: manages multiple access points and wireless networks, orchestrating them for smooth connectivity and control. Load balancer. Distribution: distributes network or application traffic across several servers to prevent any single server from becoming overloaded. Proxy server. Intermediary role: acts as a mediator for requests from clients seeking resources, providing filtering and enhanced privacy. VPN concentrators and headends. VPN management. VPN concentrators create and manage VPN connections. Headends are the receiving end of these connections in a provider's network. Collective components includes all various components connected to a network, such as computers, printers, and your devices, facilitating shared resources and communication. This structured format offers a comprehensive understanding of the different networking devices and their roles, crucial for the setup and management of a network. Overview of common networking devices. Firewall. Function: a firewall acts like a security guard for your network, checking the data entering or leaving against a set of rules. IDSIPs. Role: intrusion detection systems (IDS) and intrusion prevention systems (IPS) monitor and analyze network traffic for suspicious activities akin to a surveillance system. Router. Analogy: routers function like mail sorting centers, directing data packets to their intended destination across multiple networks. Switch. Description: switches serve as office network hubs, connecting various devices within a single network to facilitate communication. Hub and switch cabling. Functionality: cabling is the physical wiring that connects hubs and switches, forming the infrastructure for data travel within a network similar to veins in a body. Multi-layer switch. Capability combines the functionalities of both switches and routers, handling data traffic efficiently in large networks. Hub. Basic operation. A hub is a fundamental networking device that connects multiple computers but sends incoming data to all devices indiscriminately. Bridge. Purpose: Bridges connect two separate network segments, enabling them to communicate as though they are part of the same network, much like a bridge connecting two communities. DSL and cable modems. Usage: provide internet access through phone lines, DSL, and television cables, cable modems acting as gateways to the internet. Access point. Function: offers a wireless connection to a wired network similar to a Wi-Fi hotspot in a public space. Media converter. Role: translates data signals from one type of network media to another, such as from cable to fiber optics, ensuring compatibility. Voice gateway. Operation: allows voice communication to travel over the internet by converting analog voice signals into digital data. Repeater. Analogy: functions like a relay station in a broadcast network, extending the reach of a network by amplifying its signal. Wireless LAN controller. Management: manages multiple access points and wireless networks, orchestrating them for smooth connectivity and control. Load balancer. Distribution: distributes network or application traffic across several servers to prevent any single server from becoming overloaded. Proxy server. Intermediary role: acts as a mediator for requests from clients seeking resources, providing filtering and enhanced privacy. VPN concentrators and headends. VPN management. VPN concentrators create and manage VPN connections. Headends are the receiving end of these connections in a provider's network. Networked devices. This structured format offers a comprehensive understanding of the different common networking devices and their roles, crucial for the setup and management of a network. Network engineer training. In network engineering, a deep understanding of common networking devices and their roles is crucial for orchestrating an efficient, secure, and robust network. Devices such as firewalls, IDSIPs, routers, and switches form the backbone of network security and communication. Firewalls serve as vigilant sentinels, monitoring and controlling the flow of data to protect the network from threats, while intrusion detection and prevention systems IDSIPs act like a network surveillance, constantly seeking out and mitigating potential threats. Routers navigate data across the vast expanse of global networks, directing packets much like a postal service sorts mail, ensuring each bit of information reaches its intended destination. Switches function as local facilitators within networks, connecting devices within a single network segment to enable communication. The physical connectivity of a network relies on the hub and switch cabling, serving as the critical veins through which data travels. In more sophisticated setups, multi-layer switches merge the functionalities of switches and routers, optimizing data traffic and routing within large and complex networks. Hubs offer a basic form of connectivity, broadcasting incoming data to all connected devices, whereas bridges refine network structure by linking separate network segments, promoting efficient communication. Internet access is predominantly facilitated by DSL and cable modems, connecting homes and businesses to the World Wide Web through conventional phone lines and television cables. Extending network access points enable wireless connectivity, bridging wired networks to wireless devices, and allowing flexibility and mobility in Internet access. Media converters and voice gateways are specialized devices ensuring network compatibility and functionality, translating various data signals and facilitating voice communication over digital networks, respectively. In maintaining and enhancing network performance, devices like repeaters, wireless LAN controllers, and load balancers play vital roles. Repeaters extend the reach of a network by amplifying signals. Wireless LAN controllers manage and optimize wireless network segments, and load balancers distribute traffic across multiple servers to prevent overload and ensure smooth operation. Lastly, proxy servers and VPN concentrators provide critical network services, enhancing security and connectivity. Proxy servers act as intermediaries, offering resource access and additional security measures, while VPN concentrators manage VPN connections, providing secure and encrypted communication channels for remote access. Each of these devices contributes to the overall functionality and performance of a network, ensuring data is transmitted securely, efficiently, and accurately. For network engineers, proficiency in these devices and their functions is paramount, enabling them to design, configure, and manage networks that meet the ever-growing demands of our digital world. Understanding how these components work together helps in creating a network that is not only robust and secure, but also adaptable and scalable to future needs and technologies. Network device roles and connectivity. Three-tiered architecture. Structure consists of core, distribution, and access layers, organizing the network into a hierarchical model for optimized data flow and scalability. Core layer. Function acts as the network's backbone, equipped with high-speed switches and routers for rapid traffic direction. Distribution aggregation layer. Role aggregates data from access switches and routes it to the core layer, functioning like a transit hub for data packets. Access edge layer. Purpose connects devices to the network, serving as entry points like ports on a switch. Software-defined networking (SDN). Overview. SDN separates the network's control logic from the physical routers and switches, facilitating programmable network management. Application layer in SDN. Function comprises applications that communicate with the control layer to dictate network behavior. Control layer. Operation acts as the SDN's brain, directing traffic and making decisions about data routing. Infrastructure layer. Component, the physical part of the SDN, including the switches and routers that transport data. Management plane. Interface, where network administrators configure and monitor the network. Spine and leaf topology. Design, a network topology where every leaf edge device connects to every spine central node, ensuring high-speed connectivity and redundancy. Traffic flows. Patterns, the routes and patterns of data movement within a network, shaped by the network's architecture and data destinations. Data center location types. Variations ranging from on-premises to cloud-based. These locations influence network architecture and management. Storage area network SANs. Usage provide high-speed network storage to multiple hosts, crucial in large-scale storage environments. ISCSI Internet Small Computer System Interface. Protocol allows the use of IP networks for data storage by enabling SCSI commands over networks. Fiber channel and FCO. Technologies. Fiber channel is a high-speed network technology for SANs. Fiber channel over Ethernet FCO enables fiber channel to utilize Ethernet networks. Network attached storage NAS. Function, dedicated file storage that allows multiple users and diverse client devices to access data from centralized disk capacity. This structured overview provides insights into the various aspects of networking architecture, including its hierarchical structure, software-defined networking, and various storage technologies, each playing a pivotal role in modern network management and design. Network engineer training for network device roles and connectivity. Networking architecture is the structural blueprint of a network, defining the interplay of devices, connections, and protocols to form efficient, scalable, and robust systems. The three-tiered architecture is a foundational model organizing networks into core, distribution, and access layers to optimize data flow and scalability. The core layer, acting as the network's backbone, is equipped with high-speed switches and routers for rapid traffic direction, ensuring quick and efficient data transit. The distribution layer aggregates data from access switches, routing it to the core layer, functioning as a vital transit hub for data packets. Meanwhile, the access layer connects devices to the network, serving as the entry points much like ports on a switch, handling direct user access and local traffic. Software-defined networking (SDN) represents a paradigm shift in networking, separating the network's control logic from the physical routers and switches to enable more agile and programmable network management. The application layer in SDN comprises applications dictating network behavior. while the control layer acts as the SDN's brain, directing traffic and making data routing decisions. The infrastructure layer forms the physical part of the SDN, including the switches and routers that transport data, whereas the management plane provides an interface for network administrators to configure and monitor the network. The spine and leaf topology is another critical aspect, offering a design where every leaf-edge device connects to every spine central node, ensuring high-speed connectivity and redundancy. This topology supports efficient traffic flows, which are the routes and patterns of data movement within a network shaped by the network's architecture and the destinations of data packets. Moreover, the location of data centers, varying from on-premises to cloud-based, significantly influences network architecture and management. Storage area network SANs and network-attached storage NAS are crucial in large-scale storage environments, providing high-speed network storage to multiple hosts. Technologies like ISCSI allow the use of IP networks for data storage by enabling SCSI commands over networks, while Fiber Channel and FCO Fiber Channel over Ethernet offer high-speed connectivity options for SANs. Together, these components and technologies create a complex and dynamic network infrastructure essential for modern network management and design, as well as network device roles and connectivity. Understanding and effectively managing these aspects are what make network engineers integral in maintaining and advancing our interconnected digital world. Their expertise ensures that data not only reaches far and wide, but does so efficiently, securely, and reliably, meeting the ever-growing demands of technology and users. General media considerations in networking. Media connection issues. Incorrect pinout. Analogy. An incorrect pinout can disrupt network communication, similar to dialing a phone number in the wrong sequence. Bad ports. Comparison. Damaged or non-functional network ports preventing connections are like broken electrical outlets. Open short. Explanation refers to wiring faults where connections are incomplete or incorrectly connected, akin to faulty electrical circuits. LED status indicators. Function. Lights on networking equipment that indicate connection status, comparable to traffic lights guiding drivers. Incorrect transceivers. Analogy. Using inappropriate transceivers for connections is like using the wrong key for a lock. Duplexing issues. Comparison. Mismatched duplex settings causing communication failures can be likened to two people speaking different languages. TXRX reversed. Issue. Occurs when transmit and receive wires are swapped, leading to a failure in bidirectional communication. Dirty optical cables. Impact. Contamination on fiber connectors causing signal loss, similar to how a dirty lens affects photo clarity. Common tools in network setup and maintenance. Cable preparation and repair. Cable crimpers, strippers, and snip scatters. Usage. Essential tools for preparing and repairing cables, ensuring proper physical connections. Connection stabilization. Punchdown tools. Function. Devices used for securely inserting wires into punchdown blocks, stabilizing connections for reliable telecommunication. Cable identification. Tone generator. Purpose. Sensor tone through a wire to aid in identifying individual wires within a bundle. Network port testing. Loopback adapter. Usage. Test the transmit and receive functions of network ports by redirecting outgoing signals back into the system. Fiber optic cable testing. Auto optical time domain reflectometer. Function. Measures fiber optic cable integrity by analyzing light pulses sent through the cable. Electrical testing. Multimeter. Role. Measures electrical properties such as voltage, current, and resistance, crucial for troubleshooting network components. Network cable testing. Cable tester. Function. Verifies the electrical connectivity and strength of a network cable. Wire map. Purpose. Illustrates the wiring connections within a cable to help diagnose wiring issues. Network monitoring. Tab. Usage. Provides a monitoring point on a network by duplicating data signals for analysis. Fiber optic cable joining. Fusion splicer. Function joins two optical fibers end-to-end with heat, ensuring minimal signal loss. Signal analysis. Spectrum analyzer. Usage assesses signal strength and quality across different frequencies. Fiber light meter. Purpose measures light presence in a fiber optic cable to evaluate signal strength. This format provides a detailed overview of common issues and considerations in network media, as well as a comprehensive list of tools used in network setup and maintenance, each playing a vital role in ensuring efficient and reliable network operation. Network engineer training. In the intricate world of networking, general media considerations play a crucial role in maintaining efficient and reliable network operation. Issues like incorrect pinouts disrupt communication, much like dialing a wrong phone number, while bad ports act as broken conduits akin to damaged electrical outlets. Open short issues in wiring are comparable to faulty electrical circuits, disrupting the flow of data. LED status indicators serve as the guiding lights, providing immediate visual cues on connection status, much like traffic lights guide drivers. Using the wrong transceivers is akin to using an incorrect key for a lock, preventing proper connection, while duplexing issues cause communication failures similar to a dialogue in mismatched languages. When TXRX-Ys are reversed, it's like reversing the flow in a two-way street, leading to communication breakdowns. Dirty optical cables impact signal clarity in the same way dirt on a lens affects photo quality. For network setup and maintenance, tools like cable crimpers, strippers, and slip cutters are essential for preparing and repairing cables, ensuring robust physical connections. Punch-down tools stabilize connections in telecommunication systems, securing wires into punch-down blocks. Tone generators and loopback adapters aid in identifying wires and testing network ports, respectively, ensuring each component is functioning correctly. Orters optical time domain reflectometers and multimeters are vital in assessing the integrity of fiber optic cables and measuring electrical properties, crucial for thorough troubleshooting. Cable testers and wire maps verify connectivity and layout within cables, diagnosing issues at the core. In monitoring and maintaining network health, taps provide essential data points for analysis, duplicating signals for in-depth examination. Fusion splicers join optical fibers with precision, ensuring minimal signal loss for uninterrupted data flow. Spectrum analyzers and fiber light meters assess signal strength and quality, crucial for ensuring that data travels effectively across the network. Understanding and effectively managing these media considerations and utilizing the right tools are what make network engineers essential in today's interconnected world. Their expertise ensures that networks not only function smoothly, but are also prepared to meet the challenges and demands of ever-growing digital communication needs. From the physical layer of cables and connectors to the analytical tools that assess and ensure network health, each component and tool is a critical piece in the complex puzzle of network architecture and maintenance. Network cable types for diverse networking needs. Twisted pair cabling. Twisted pair cabling, comprising pairs of wires twisted together, minimizes electromagnetic interference. Most local network installations commonly use it for its suitability and efficiency. Fiber optic cables. Fiber optic cables transmit data using light, making them ideal for high-speed, long-distance communication. They excel in environments requiring fast data transfer over significant distances. Coaxial cables. Coaxial cables feature an inner conductor surrounded by an insulating layer and shield. They work well for high-frequency electrical signals commonly used in various settings. Twinaxial cables. Twinaxial cables with two inner conductors within a common insulating layer provide higher bandwidth and reduced interference. They are perfect for short-range, high-speed applications, outperforming coaxial cables in certain scenarios. Fiber optic cables. Fiber optic cables utilize light for data transmission. Offering higher bandwidth and longer distance transmission, they remain immune to electromagnetic interference, unlike traditional cables. Plenum vs PVC cables. Plenum cables, known for being fire retardant, are used in building plenum spaces. On the other hand, PVC cables are less expensive but emit toxic fumes when burned, making them less suitable for certain environments. Understanding fiber standards. Network engineers often encounter various fiber standards, each tailored for specific networking needs. 10BASE-T, an Ethernet standard, offers 10 Mbps bandwidth over twisted pair cables such as Cat3 or higher, supporting lengths up to 328 feet 100 meters. 100BASE-TX, a fast Ethernet standard, provides 100 Mbps bandwidth, usually over Cat5e cabling, maintaining signal integrity up to 328 feet. 1000BASE-T, a gigabit Ethernet standard, achieves 1 Gbps over Cat5e or higher copper wiring with a distance limit of up to 328 feet. 10GBASE-T, delivering 10 Gbps Ethernet over Cat6a or Cat7 twisted pair cabling, transmits up to 180 feet with Cat6 and up to 328 feet with Cat6 a Cat7. 40GBASE-T supports 40 Gbps Ethernet over twisted pair cabling, reaching up to 98 feet with Cat8 cabling. 1000BASE-LX, a long wavelength gigabit Ethernet over fiber, covers up to 16,404 feet with single-mode fiber and up to 1,804 feet with multi-mode fiber. 1000BASE-SX, suited for short wavelength signals over fiber optic, handles distances up to 1,804 feet on multi-mode fibers. 10GBASE-LR, a 10 gigabit Ethernet standard for long reach over single-mode fiber, transmits data up to 32,808 feet. 10GBASE-SR, ideal for short reach on multi-mode fiber, manages distances up to 1,312 feet with 10 Gbps Ethernet. Practical applications of cable types in network engineering. In network installations and communications, selecting the right type of cable is crucial. Here are typical scenarios for each cable type. Twisted pair cabling is most commonly found in local area networks LANs in office buildings, homes, and schools. It's favored for its affordability and ease of installation. Fiber optic cables are mainly used in backbone network structures due to their capability for high-speed, long-distance data transmission. Coaxial cables are often chosen for cable television systems, broadband internet, and some data networks. Twinaxial cables excel in environments like server rooms or data centers where high-speed connections between switches and storage devices are critical. Plenum cables are essential in building plenum spaces for their fire-retardant properties, while PVC cables find their place in less regulated areas due to their lower cost. Each of these cables and standards has a specific role, chosen based on network requirements like speed, distance, budget, and environmental considerations. Network engineers must understand the best applications for these different cables and standards to build efficient, reliable, and scalable networks. 1. Cable crimpers, strippers, and snips cutters, tools used to prepare and terminate network cables. 2. Punch-down tools, a device used to insert and secure wires into punch-down blocks, creating a stable connection. 3. Tone generator, a tool that sends a signal through a wire, allowing technicians to trace and identify cables. 4. Loopback adapter, a device that plugs into a network port and crosses over the transmit and receive pins, used for testing and troubleshooting. 5. Optical time domain reflectometer, a sophisticated instrument used to test the integrity of fiber optic cables by sending pulses of light into the cable and measuring reflections. 6. Multimeter, an electronic measuring instrument that can measure voltage, current, and resistance. 7. Cable tester, a device that checks the electrical connections in a signal cable or other wired assembly. 8. Wire map, a diagram or tool used to show the electrical connections in a cable. 9. Tap, a device inserted at a specific point in a network to monitor the data passing through the network. 10. Fusion splicer, a device that joins two fiber optic cables together by melting or fusing them. 11. Spectrum analyzer, a device used to examine the frequency spectrum of radio frequencies, aiding in troubleshooting and optimizing networks. 12 Fiber Light Meter, a tool for measuring the amount of light present in a fiber optic cable to ensure optimal signal strength. Network engineer training with troubleshooting tools. In the dynamic field of network engineering, a range of specialized tools are essential for installing, maintaining, and troubleshooting various network components. These tools are the lifeline of technicians and engineers, ensuring networks are reliable, efficient, and secure. Cable crimpers, strippers, and snips cutters are fundamental in preparing and terminating network cables. Crimpers are used to attach connectors to the ends of cables. Strippers remove the outer insulation without damaging the wires, and snips or cutters are used to trim the cables to the desired length. These tools are vital for making and repairing Ethernet cables in offices, data centers, and installation sites, ensuring a robust physical connection. Punch-down tools are used to securely insert wires into punch-down blocks, creating stable connections in telephone and data panels. They're essential in structured cabling, where maintaining a solid and reliable connection is paramount, especially in commercial and residential buildings' telecommunications rooms. Tone generators are used alongside probes to trace and identify specific cables in a bundle, helping technicians avoid confusion and errors in complex wiring environments. They're particularly useful in large data centers or when servicing older buildings with numerous unmarked cables. Loopback adapters are simple yet effective tools for testing and troubleshooting network ports. By crossing over transmit and receive pins, they allow technicians to diagnose issues with network cards or ports in routers and switches, ensuring the hardware is functioning correctly before addressing software or configuration issues. ODDA's optical time domain reflectometers are sophisticated instruments crucial for maintaining the integrity of fiber optic cables. They send pulses of light into the cable and measure reflections to identify faults or breaks. Technicians rely on ODDAs for deploying and maintaining long-distance fiber connections in metropolitan networks or between data centers. Multimeters are versatile tools for measuring electrical properties such as voltage, current, and resistance. They are indispensable for troubleshooting power issues, verifying network voltages, or testing battery levels in backup systems. Cable testers and wire maps verify the electrical connections in signal cables, ensuring each wire is correctly placed and securely connected. These tools are particularly useful in ensuring the quality and integrity of Ethernet cables, crucial for reliable network performance. Taps provide a non-intrusive way to monitor network traffic, allowing technicians to diagnose issues or analyze performance without disrupting the network. They are often used in security applications or performance monitoring. Fusion splicers are used in fiber optic installations to join two fiber cables end-to-end, ensuring minimal signal loss and optimal connection quality. They are essential in field repairs or when extending fiber networks. Spectrum analyzers and fiber light meters are used to optimize and troubleshoot networks. Spectrum analyzers help identify interference or optimize wireless networks by analyzing radio frequencies. In contrast, fiber light meters measure the light present in fiber optic cables, ensuring the signal strength is within optimal ranges for data transmission. Understanding and efficiently using these tools allows network engineers to install, maintain, and troubleshoot networks effectively. Whether preparing cables, tracing connections, testing network components, or optimizing data flow, these tools are essential in ensuring network reliability and efficiency, making them indispensable in the network engineer's toolkit.